Welcome dear learners. We are continuing the course Quantum Chemistry. In this module, we are focusing hybridization, quantum mechanical treatment. The contents of this module include hybridization, its definition and various aspects, quantum mechanical treatment of sp hybridization, and the quantum mechanical treatment of sp2 hybridization. First of all, we are discussing hybridization. You are all familiar with the term hybridization. Whenever we are seeking a water molecule, it is associated with sp3 hybridization. If you are having CH4, it is also sp3 hybridization. Whenever you are dealing with a molecule of BCl3, it is having sp2 hybridization. So, hybridization is a very popular concept from chemistry. And now in this section, we are focusing on the quantum mechanical treatment of, quantum mechanical aspects of hybridization. Quantum mechanics helps to find out the hybrid orbital wave functions, the coefficient of linear combination, and every aspects associated with the hybridization. So, we are giving focuses to the quantum mechanical aspect of the hybridization. First of all, hybridization. Linus Pauling was the scientist who introduced the theory of hybridization, and it was in the year 1931. And Linus Pauling introduced this concept of hybridization to explain the structure of simple molecules using atomic orbitals. And by definition, hybridization is the intermixing of atomic orbitals of nearly same energy to get a new set of orbitals called hybrid orbitals having identical shape and energy. Suppose we can take the case of sp hybridization. You know the fact that s orbitals are spherically symmetrical and p orbital is dumbbell in shape. So, in an sp hybridization, one s orbital combine with or mix with p orbital. As a result, we are getting a set of two hybrid orbitals. So, these two hybrid orbitals have identical energy and shape. So, you are getting first hybrid orbital like this. This is the hybrid orbital, first hybrid orbital. And the second hybrid orbital can be represented like this. This is the second hybrid orbital. So, hybridization is defined as the mixing up of atomic orbitals of nearly same energy. It should be noted that in sp hybridization, the participating orbitals are s orbital and p orbital, and they must have nearly same energy. There should not be large difference in energy. It is one of the important conditions of hybridization. So, hybridization is the mixing up of orbitals of nearly same energy to get a set of hybrid orbitals. These two hybrid orbitals have the same shape, identical shape as well as identical energy. That all about the definition of hybridization. Now, we are focusing on some important features or salient features of hybridization. The number of hybrid orbital formed, is equal to the number of atomic orbitals which undergo hybridization. This point I already just mentioned. If we are taking sp hybridization, one s orbital and one p orbital will take part in hybridization. As a result, you are getting two sp hybrid orbitals. In the case of sp2 hybridization, there are a total of 3 participating atomic orbitals. They are one s orbital and 2 p orbital. So, in this sp2 hybridization, 3 orbitals are take part, and as a result, we are getting 3 sp2 hybrid orbital. Suppose we are taking another hybridization, that is sp3d hybridization. In sp3d hybridization, 5 orbitals are take part in hybridization. They are one s orbital, 3 p orbitals and 1 d orbital. A total of 5 orbitals are take part in hybridization. As a result of that, we are getting 5 sp3d hybrid orbital. So, this statement, number of hybrid orbital formed is equal to the number of atomic orbitals which undergo hybridization. Next important feature, the sigma bonds formed with hybrid orbitals are more stable than those formed with pure orbitals. That is, let us consider the case of a CH4 molecule. In the case of a CH4 molecule, the hybrid orbital used in the formation are sp3 hybridization is shown by carbon center, and this sp3 hybrid orbital of carbon form sigma bond with 1s orbital of hydrogen. So, there do a hybrid orbital formation during the generation of CH4 molecule. That is, the CH bond formed is having high strength compared with the bond which is produced from pure orbitals. Suppose we are taking H2 molecule. This H2 molecule is generated by the overlapping of 1s orbitals each from hydrogen atom. That is a sigma bond generated from a pure atomic orbital. But in CH4, the CH bond is formed from sp3 hybrid orbital of carbon and 1s orbital of hydrogen. So, this CH bond is having high strength when compared with the sigma bond produced from pure orbitals. Now, hybridization invariably involves atomic orbitals of the same atom. For instance, if you are taking water, hybridization is generally specified with respect to the central atom. In water, the central atom is oxygen and the oxygen atom shows sp3 hybridization. So, hybridization invariably involves atomic orbitals of the same atom. This point is highly significant. We are continuing the salient features. Effective hybridization occurs only when the orbitals undergoing hybridization are of similar energy. This point is highly significant. The participating orbitals must have nearly same energy. The electronic charge in hybrid orbital is concentrated more in one direction, and this property, this feature leads it to a better overlap with orbitals of other atoms. Hybrid orbitals generally form either sigma bonds or contain lone pair of electrons. This means hybrid orbital will not form or do not form pi bonds. The stability of bonds formed by hybrid orbitals is due to excessive overlapping of orbitals provided by them. So, strength proportional to overlapping. Hybrid orbitals impart very strong or excessive overlap. So, bond formed as a result of such overlap will be strong. Now, we are taken into consideration of quantum mechanical treatment of sp hybridization. That is, how quantum mechanics consider sp hybridization. We are discussing every aspect of sp hybridization, every quantum mechanical aspect of sp hybridization. Quantum mechanics provides a fundamental framework for understanding the concept of atomic and molecular hybridization, which plays a crucial role in explaining the structure and bonding of molecules. Hybridization theory is a model used to explain the mixing of atomic orbitals to form new hybrid orbitals during the formation of chemical bonds. Quantum mechanics help us to understand the energy and spatial distribution of hybrid orbitals. It should be noted that in the case of sp hybridization, the result is two sp hybrid orbitals, and these two sp hybrid orbitals aligned or take linear geometry. That is, these two hybrid orbitals are placed along a line. That is, the resultant molecule, the molecule with the sp hybridization has linear geometry. Similarly, if we are taking sp2 hybridization, then the resultant 3 sp2 hybrid orbitals will arrange towards 3 corners of a triangle, and hence we can say that the resulting molecules will have trigonal planar geometry. One more example, consider sp3 hybridization. In the case of sp3 hybridization, one s orbital and 3 p orbital take part in hybridization. As a result, we will get 4 sp3 hybrid orbitals. These 4 sp3 hybrid orbital will arrange towards 4 corners of a regular tetrahedron, and the intermittent angle is 109 degree 28 minute. Thus, the molecules possessing sp3 hybridization will exhibit tetrahedral geometry. For example, CH4 molecule is a perfect tetrahedral shaped molecule. The process involves the quantum mechanical treatment of hybridization involves the Schrodinger equation for the entire molecule writing up and the solution to that Schrodinger wave equation. That is, the quantum mechanical treatment is simply the solving of the Schrodinger wave equation for the entire molecule. And these solutions account for electron-electron repulsion and the electrostatic attraction between electron and the nucleus. Quantum mechanics enable the calculation of coefficients of atomic orbitals used in hybridization, and also enable the hybrid orbital wave functions. So, to get the coefficients of atomic orbitals used in hybridization and to get hybrid orbital wave function, we must apply the quantum mechanical treatment. Quantum mechanics provides the theoretical framework to explain the concept of hybridization in terms of wave functions of electrons and the formation of new hybrid orbitals. The wave functions for hybrid orbitals or hybrid orbital wave functions is another important part of the quantum mechanical treatment. The wave functions for hybrid orbitals are obtained by taking linear combination of the angular wave functions of the appropriate atomic orbitals. The wave function for ith hybrid orbital formed from s and p atomic orbitals is given by phi I equal to AIS plus BIPX plus CIPY plus DIPZ. It should be noted that the coefficients AI, BI, CI, DI are termed as coefficients of hybrid orbital wave functions, coefficients of atomic orbitals in the hybrid orbital wave functions, and quantum mechanics enable the calculation of these coefficients, and also S, Px, Py and Pz represent the atomic orbital wave functions. So, hybrid orbitals are obtained by the linear combination of atomic orbital wave functions. The coefficients AI, BI, CI and DI can be determined by using a set of rules, and we are now illustrating the rules which help us to evaluate the coefficients. The first rule, each wave function is individually normalized. Each wave function is individually normalized. This implies that AI square plus Bi square plus Ci square plus Di square equal to 1. Moreover, each hybrid orbital in the set of hybrid orbitals must be orthogonal to other hybrid. That is, the first hybrid orbital is orthogonal with the second hybrid orbital and so on. Now we can take two hybrid orbital psi I and psi j, and as a result of their orthogonal nature between psi I and psi j, we can arrive at this conclusion: Ai Aj plus Bi Bj plus Ci Cj plus Di Dj equal to 0. The squares of the coefficients of any component atomic function summed over all the hybrids in which it participate must be equal to unity. That is, sigma Ai square is equal to 1. So, by using these sets of rules, it is possible to evaluate the coefficient of atomic orbitals in hybrid orbital wave functions. With the help of the above rules, the following procedure is employed to generate the equivalent hybrid orbitals. As the first step, we have to choose a Cartesian coordinate and place on the ith hybrid orbital along one coordinate axis, and as many of other orbitals as possible in the plane containing this axis and other coordinate axis. Since the s orbital has a spherical symmetry, it should be noted that equivalent hybrid orbitals of a set contain 1 by n of the total of the unit s orbital and distributed in n hybrid orbital. Simply say that the coefficient of each hybrid orbital for s orbital is 1 by root n. Now we are looking on sp hybridization. As I already mentioned, sp hybridization involves the hybridization of s orbital and p orbital to get a set of two hybrid orbitals having identical energy and shape. The sp hybridization is where when one s orbital and one p orbital intermix to form two sp hybridized orbital as shown here. This is one s orbital and this is one p orbital. They are going to mix together, and that mixing up process is termed as the hybridization, and as a result of their mixing up, we are getting two products. They are two sp hybrid orbitals. This is first sp hybrid orbital, this is the second sp hybrid orbital, and they can clubbed together to get an arrangement like this, and these two hybrid orbital take an angle of 180 degree, and thus it can be concluded that molecules with the sp hybridization will be linear with the bond angle 190 degree. Moreover, the molecules formed are linear and have a bond angle of 90 degree. The sp hybridized orbital has an equal distribution of s and p orbital characteristics. That is 50% s character and 50% p character. Now we can take sp2 hybridization. Here there is only 33.3% s character and 66.6% of p character. So if you are taking sp3 hybridization, it is having only 25% of s character and remaining 75% will be the p character. But in the case of sp hybridization, s character and p character will be 50-50. That is 50% s character and 50% p character. Percentage of s character has a strong connection with the acidity of the molecule. For instance, I am taking three molecules in order to illustrate this percentage characteristics. I am having three molecules, that is CH triple bond CH. Next one is CH2 double bond CH2 ethylene. And the last molecule is CH3 single bond CH3. This is saturated compound, this is ethane, and this is ethylene. My question is, what about the acidity of these three compounds? It should be noted that with the increase in percentage of carbon, the acidic strength also increases. In CH triple bond CH, the hybridization shown by the carbon atom is sp, and here the hybridization shown by the carbon atom is sp2, and in this case the hybridization of carbon atom is sp3. In sp3 case 25% of s character, in sp2 case 33.33% of s character, and in sp case 50% of s character. Higher the percentage of s character, more will be the acidic strength. Hence, we can conclude that CH triple bond CH is more acidic than CH2 double bond CH2, which is again acidic than CH3 single bond CH3. Now, we shall proceed into hybrid orbital wave functions of this simple hybridization, that is sp hybridization. The wave functions for sp hybrid orbitals. I already mentioned the fact that the hybrid orbital wave function can be represented as a linear combination of atomic orbital wave functions. In order to illustrate the quantum mechanical treatment of sp hybridization, we are considering an example for a molecule with sp hybridization. The molecule is beryllium hydride BeH2. The central atom beryllium exhibit sp hybridization, that is one s orbital from beryllium combines with or overlap with one p orbital of the same beryllium to form two sp hybrid orbital, that is the molecule beryllium hydride is a good example for molecule showing sp hybridization. And based on the principle of linear combination of atomic orbitals, quantum mechanics insists us to represent two sp hybrid orbital wave functions as a linear combination. So, imagine in BeH2 molecule, a 2s orbital and a 2px orbital are taking part. Thus, we have to get two sp hybrid orbitals because number of orbital take part in hybridization equal to number of hybrid orbital produced. So, these are the two wave functions of the hybrid orbitals. I mark it as psi sp1 and psi sp2, and hybrid orbital must be linear combination of atomic orbital. Thus, I am writing psi sp1 is equal to a1 2s plus b1 2px. Similarly, psi sp2 is equal to a2 2s plus b2 2px. Here 2s and 2px are atomic orbital wave functions. Hybrid orbital wave functions are obtained by the linear combination of atomic orbital wave functions. Hence, we are getting these two equations. Moreover, we know the fact that s orbital is equally distributed or symmetrically distributed. Therefore, the coefficient of s orbital can be represented as 1 by root n, where n represents the total number of hybrid orbitals. So, a1 square is equal to a2 square is equal to 1 by 2, or simply you can say that a1 equal to a2 equal to 1 by root 2. If there are n hybrid orbitals, coefficient of s will be 1 by root n. Here there are two hybrid orbital, so coefficient of s orbital will be 1 by root 2. Hence, a1 equal to a2 equal to 1 by root 2. The wave functions are continuing. It should be noted that the wave function psi sp1 is normalized. We know the condition for normalization. Integral psi star rt psi of rt d tau is equal to 1. This is the condition for normalization. So, instead of psi rt, I am taking psi sp1. So, integral psi sp1 into psi sp1, since we are discussing real part of the wave function, integral psi sp square 1 d tau, and that is equal to a1 2s plus b1 2px the whole square dx. On simplification we are getting this final equation, a1 square into integral 2s square d tau plus b1 square into integral 2px square d tau plus 2a1 b1 integral 2s 2px d tau is equal to 1. Since the atomic orbitals are individually normalized and mutually orthogonal, we can write this expression integral psi square sp1 d tau equal to a1 square plus b1 square plus 2a1 b1, that is equal to a1 square b1 square equal to 1. Since a is equal to 1 by root 2, b also 1 by root 2. Why a is 1 by root 2? This is because the coefficient of s orbital in n hybrid orbital will be 1 by root n. Here we are having more than one hybrid orbital, and the coefficient of a will be, here we are having two hybrid orbital and the coefficient of a will be 1 by root 2. A represents the coefficient of s orbital. Moreover, the two sp hybrid orbital wave functions are psi sp1 and psi sp2. These two wave functions are mutually orthogonal. We know about the condition for orthogonality. Integral psi I star psi j d tau will be 0. This is the condition for orthogonality. So if I am taking psi sp1 as psi I and psi sp2 as psi j, then integral psi sp1 star psi sp2 d tau must be 0. And this leads to the equation a1 a2 plus b1 b2 is equal to 0, and we have to substitute for a1 a2 and b1 such that 1 by root 2 into 1 by root 2 plus 1 by root 2 b2 is equal to 0, or we will get the value of the coefficient b2. b2 is equal to minus 1 by root 2. Thus, by applying the quantum mechanical principles, we got the two hybrid orbital wave functions of sp hybridization, and the two sp hybridized, the hybrid orbital wave functions of two sp hybrid orbitals are psi sp1 is equal to 1 by root 2 into 2s plus 2px, and psi sp2 is equal to 1 by root 2 into 2s minus 2px. That all about the quantum mechanical treatment of sp hybridization. Now we are moving on to the quantum mechanical treatment of sp2 hybridization. As the name indicate, in sp2 hybridization, one s orbital and two p orbital hybridize to form three sp2 hybrid orbital. Number of orbital take part in hybridization equal to number of hybrid orbital produced. Here one s orbital and two p orbital mix together to produce three sp2 hybrid orbitals. And in the case of three sp2 hybrid orbitals, or taking a single sp2 hybrid orbital, there is a percentage of s character and p character. S character is nearly 33% and p character is 67%. This is the pictorial illustration of sp2 hybridization. One s orbital combines with the two p orbital. Let the two p orbitals are px and py. So 2s combines with the 2px and 2py to produce 3 sp2 hybrid orbital. These 3 sp2 hybrid orbital are aligned towards the three corners of a regular triangle, and hence the resultant molecule will be trigonal planar. The molecules formed are trigonal planar and have a bond angle of 120 degree. We shall now proceed into hybrid orbital wave functions of sp2 hybridization. Now, in order to illustrate the quantum mechanical principles to sp2 hybridization, first of all, we shall take an example of molecule with sp2 hybridization, that is BF3 molecule. BF3 molecule, in BF3 molecule, the central atom boron exhibit sp2 hybridization. And according to linear combination of atomic orbital principle, the three sp2 hybrid orbitals can be represented as psi sp21 equal to a1 2s plus b1 2px plus c1 2py, and psi sp22 is equal to a2 2s plus b2 2px plus c2 2py, and finally psi sp23 is equal to a3 2s plus b3 2px plus c3 2py. Since the s orbitals are symmetrically distributed or equally distributed, a1 square equal to a2 square equal to a3 square equal to unity. That means a1 equal to a2 equal to a3 equal to 1 by root 3. This is another important application. Assume that psi sp21, the first hybrid orbital wave function, point towards x-axis. Hence, this orbital will have a contribution from 2s and 2p orbital only. No contribution from 2px or 2py. Hence, the contribution of 2py orbital will be 0, so that C1 is equal to 0. Next point, psi sp1 is normalized. This condition for normalization leads to the result a1 square plus b1 square plus c1 square equal to 1, or a1 square plus b1 square is equal to 1. Since a1 is equal to 1 by root 3, hence b1 equal to root of 2 by 3. Let psi sp21 and psi sp22 are orthogonal, and psi sp2 and psi sp23 are also orthogonal. These two sets of orthogonality between psi sp21 and psi sp22, other set of orthogonality between psi sp21 and psi sp23, we can arrive at the following two important relations. If we are taking first and second, then I can mark it as a1 a2 plus b1 b2 is equal to 0. Similarly, if I am taking the first hybrid orbital wave function and third hybrid orbital wave function, we can write a1 a3 plus b1 b3 equal to 0. Based on this, we can calculate the value of b2 as well as b3. b2 is equal to minus a1 a2 divided by b1. Once substituting the known values, we are getting the value of b2 is equal to 1 by root 6. Similarly, b3 equal to minus a1 a3 divided by b1, that is equal to minus 1 by root 3, 1 by root 3 under root of 2 by 3. And this leads to the value of b3 as minus 1 by root 6. Moreover, psi sp2, each function is individually normalized, that I already mentioned. Psi sp22 is normalized such that I can write a2 square plus b2 square plus c2 square is equal to 1, or c2 square is equal to 1 minus of a2 square plus b2 square, that is equal to 1 minus 1 by root 3 plus 1 by root 6, and the final result is the coefficient c2 is equal to plus or minus 1 by root 2. Moreover, psi sp23 is a normalized wave function. Thus, I can write a3 square plus b3 square plus c3 square is equal to 1. Also, c3 square is equal to 1 minus a3 square plus b3 square, that is equal to 1 minus 1 by 3 plus 1 by 6, that is equal to 1 by 2. Hence, c3 is equal to root of 1 by 2, that is 1 by root 2. Let c2 have a positive value, then the value of c3 will have to be negative. This is because orthogonality of psi sp21 and psi sp23 to get a2 a3 plus b2 b3 plus c2 c3 equal to 0. Thus, we go to the coefficient c2 equal to plus 1 by root 2 and c3 equal to minus 1 by root 2. So, we got all coefficients for sp2 hybridization, and by putting all these coefficients and atomic orbital wave functions, we will get 3 sp2 hybrid orbital wave functions of the system, and that sp2 hybrid orbital wave functions are psi sp21 equal to 1 by root 3 2s plus root of 2 by 3 2px. Psi sp22 is equal to 1 by root 3 2s minus 1 by root 6 2px plus 1 by root 2 2py. And finally, psi sp33 is equal to 1 by root 3 2s minus 1 by root 6 2px minus 1 by root 2 2py. These are three important hybrid orbital wave functions of sp2 hybridization. There are so many molecules exhibiting sp2 hybridization. So many molecules will have trigonal planar geometry, BF3, BCl3, BBr3, BA3, BH3. So many molecules will exhibit the sp2 hybridization. In sp2 hybridization, one s orbital and two p orbitals are taking part to produce three sp2 hybrid orbitals, and the sp2 hybrid orbitals have arrangement trigonal planar. So molecules with sp2 hybridization do exhibit trigonal planar geometry. That all about the quantum mechanical treatment of sp2 hybridization. Hence, in this module, we focused basic aspects of hybridization, quantum mechanical treatment of sp hybridization and sp2 hybridization. Have a very nice learning experience. Thank you.